how you can tell is this little thing down here. This indicates how long it's been recording. So if you don't see that someday, say, hey, you forgot to do screencast-o-matic. All right, let's go back to current slide. And I think we hit this last time, didn't we? It was my memory we did. Okay, now, not only, here's what reminded me I didn't have it done. Not only does screencast-o-matic record what's projected, it also records what I'm saying. That's why the sound was in there. But it does it in sync. And it's not just what's on the slideshow, because you see this computer has an ionizing pen, and I can write on here. I've got to get my pen set up. Okay, I like a darker color than red. And from Galileo's, that's equal to 4.9 t squared. Okay, and that's measured in meters. Comes from, and I think that's what exactly mine. Didn't we actually do exactly mine? I'm pretty sure we did, didn't we? So this is, exactly one. Okay. So this did not show any of that. Sorry about that. When you get to the YouTube videos, you'll see all this has already been done. Sorry about that. This I found one of the weirdest representations of what's going on here. I don't know why they do That makes sense. Somewhat. Now, let's take that curve and that secant line, and let's do something else. Okay? This is the average same curve, what we're going to do here, yep, is this. Can't write it when I'm blown up like this. So do you prefer the expanded view or me to write the formula? Are you okay? Which way you want it? Can't help us. Would you rather see the formula written over here too? You don't care. Okay. Alright. So remember what the this side here, you already had that. As long as you have a fixed delta t, the slope of the secant line is delta S over delta t. You understand the symbology, right? As the delta t is approaching 0, guess what? The delta S is also approaching 0. So when you get a 0 over 0, it used to be anything divided by 0 was called it undefined. Can't do it. Now we're going to introduce the concept as if the numerator is also approaching 0, the denominator is 0. Now we call that not an undefined form, but an indeterminate form. Does it matter if the denominator is going to 0 so much faster than the numerator? Then maybe this is undefined. But if we're going about the same speed or speed or something, then maybe it does have to go. That's what we're talking about today. Limit as delta t approaching 0 to the denominator, what is that ratio? Okay? The rise of the run. That is true. Okay. I feel like we did most of that last time too, didn't we? Oh, we did. Okay. I didn't remember the guy riding up. So I think we're about the right place. Now, okay. This is example 2. You're not quite ready for example 2 yet, but let's back up a little bit. Velocity is only one of the many examples of rate of change. Now, so far I see one text and a e-text. Oh, I usually see a note there. Okay. Oh, you got it for this too. Okay. Since some of them don't have this, I'm going to do a bit more than I normally would do in here. Velocity is only one of many examples of a rate of change. Our reasoning applies to a quantity, any quantity y that depends on any quantity x. Y is a function of x. So y is equal to some f of x. Okay? For any interval x0 to x1. Now, y'all are familiar with interval notation, right? Okay. I really don't like it, but it is fairly shorthand and easy to write. Okay? We can set the delta F, which is this, change of F, that would be F of x1 minus F of x0. Now, are y'all familiar with the delta T? That's what delta means. Yep. It's always set. There's your delta F. Okay? Your delta X, the independent variable, that would just be x1 minus x0. Again, always put final minus initial. So then we can talk about the average rate of change of this function, whether it's talking about time or not. It doesn't have to be talking about velocity. It could be anything. Miles per gallon. It could be cubic feet. Well, that's time again. Cubic feet per minute. Any kind of things that's changing with respect to some other variable. Then the average rate of change, well, I'll abbreviate this, average rate of change, okay, would be delta F over delta X, which would be F of x1 minus F of x0 over x1 minus x0. There would be your average rate of change. Average rate of change. Now, if we want to take the rate of change, here's what we do. Doesn't produce it, okay? It's produce. What happens is those rate of change. If that doesn't produce rate, if it does have a limit, what would be the independence of its limit? Okay? Now, we're going back to speed, okay? We talked about it being other things. We're going back to time being the interval here. And let's go and clear this out of the way. Example 2, the speed is found in air. Here's the formula. No, this isn't got to do with that. It has to do with speed, but it's not changes in place over transit time. V, velocity, as found in air, is equal to 20 times the square root of capital T. Okay. You might say, oh, isn't that time? Okay. Any of you have statistics yet? Okay, little t is time. Capital T is temperature. Okay? And a lot of times in physics, that's always going to be Kelvin. This one, it doesn't. Yes, it is. Okay, it is within the geometry. Okay? So the approximate speed is found in air. So this is the velocity anyway. The 20 has to have some units to it. Meters per second per say 1/2. But hey, that we might just make it in cents, but we have to do. So they're not measuring in units. Okay. Estimate the instantaneous rate of change of V with respect to T at the temperature when T is equal to 273. Does anyone know what 273 is? 273. Okay, what's that? 0 Celsius, exactly. Freezing point of water. Okay, that's 273 K. Okay? And so this is going to be our T0. Everything's going to be compared to this. Alright? Now, we're going to do something a little different than before. The first one to work is the lower. So, what we do is we start with okay? That would be meters per second. Now, I'm just assuming that it didn't say that, yeah, 1 meter per second. Okay? So that speed is found at freezing point of water. 0 degrees Celsius, 32 Fahrenheit. Speed is found in there. Now, what do you reckon happens when the speed is found and the temperature goes up? Oh, you've never changed. But it does change. Velocity does increase the temperature with sun. What we want to do is see by how much. Now, what we're going to do, what's the area of the slightly below 0.9. That's even worse. Okay, what's wrong with that picture? We have the temperature speed going up as the temperature is decreasing. It should be going down as the temperature decreases. So one of these is wrong. 330.15, I will buy that one, okay? Let me purchase that one, okay? 330.15, okay? Before you stop talking a little bit, okay, now you change the velocity now is 0.3 divided by the then they go to the other side. Okay? And if my voice is well, which was D is equal to 20 times the root of capital T. This is something that some people have had debate. If anyone has ever heard of this, I haven't. For some reason, while over the weekend, I was trying to get things to load. It said I needed to update my Adobe. So I thought, well, let me do that. As soon as I started trying to do that, I started getting these messages here. And let's see if this will count. Okay. All right. Basically, your average rate of change is 20 times the root of T1 minus 20 times the root of T0. And just let the calculator hang on to all the digits over T1 minus T0. Okay. And in this case, well, what did we get last time? 6.523. Don't be something in between those two, approximately. Okay? This is 1/100th of a K off, and this is 100th of a K. So if they're between those two, it looks like 0.60525 would probably be a very good guess. Okay? Get exact and not exact. You want to see what it is exactly? I cheated last time and showed you how to do this already again. Take it, no, let's just, we'll hold on. Alright, so you see, both ways, something around 0.605 to something. Alright, so we have a pretty good warm and fuzzy feeling about that subject. Delta T, the step now, is going to 0. It shows those results as here is the see how, in a sense, visually how limits work on the graph. How they work in the paper, numerics. Okay? That's what we talked about before. Just making sure that you're backing it out. Okay? And by the way, one more little quote back here. How did we have to take on? Tell me about the limits of that. Linear function. We'll go back and say this again in another context. For a linear function, f of x is unintended value let's pick 2 points here. X 0 going to x1. Okay? So that would be alpha x1 minus alpha x0 divided by x1 minus x0. Right? That would be your additive vector. So, the f of x1 would be mx1 plus b minus mx0 plus b, right? Over x1 minus x0. Okay? Clearing parentheses a little bit, that'd be mx1 plus b minus mx0 minus b over x1 minus x0. By that? Everybody in agreement? Well, guess what? Plus b minus b over b. Right? So then we have m x1 minus m x0 in the numerator, x1 minus x0 in the denominator. I can factor out the m here. What does that leave me with? x1 minus x0 over x1 minus x0. Guess what the limit is? M is the same. It's the same no matter what. x1 and x2 or x7 or x1. What's both? There is a summary at the end of every section. The lady who picked this text to be the one that you use, she loves the summary, so I say review that. You got it. I kind of like the preliminary questions. Okay? So let's take a look at those, and there's some where you don't have it. So have your choice. So I'll read them for you. The first average velocity is equal to the slope of the improvement line between 2 points on a graph. Average velocity is equal to the slope of the improvement line between 2 points on a graph. What graph are you talking about? nebulous kind of a question like this, but I guess we want to illustrate it to begin with. Of a position as owner, having washed and extracted the Number two, can instantaneous velocity be defined as relation? Yea or no? No. The limit of relation is not there yet. Simple stuff. Why can't it? If not, how is instantaneous velocity computed? By velocity. Okay, it's got a limit. So, no instantaneous velocity is defined as the limit of the relative velocity at the time of that instance. Number three, what is the graphical interpretation of the instantaneous velocity at the moment t is computed? What's the graphical interpretation of that instantaneous velocity? Four, what is the graphical interpretation of the following statement? The average rate of change approaches the instantaneous rate of change as the interval exited at constant is executed. What is the graphical interpretation of that statement? Average rate of change approaches the instantaneous rate of change as the interval. Both of the ticket line over here have the x0 to x1, but both equate to the space line at x0. Number five, the rate of change of atmospheric temperature with respect to altitude is equal to the slope of the transatmospheric graph. This graph. What would be your action then? The rate of change of atmospheric temperature with respect to altitude. What would you put on this graph? Rate of change of atmospheric temperature with respect to altitude is equal to the slope of the transatmospheric graph. What's that? That's the question. What is the function of that rate? Exactly, Calvert. Okay? And what
Homework exercises here, and if you don't have to book yet, you're welcome to take a picture of mine, but I will take a picture of it. End of the eyes, 1 through 9, and end of the eyes, 11 through 17, and then end of the eyes, 19 some of those are just listening to or writing to especially those last two. The main calculations are in sections. So 29 and 31. Which is still a good idea to do. Now also, every time I see some of these, I like to look to see if there might be something that would suggest that maybe we should take it back. I thought I saw something that was understood that it was something that funded material reporting that's here the tax price. If you find something like that, you would tell us to do it in one way. There are also always further impact problems. There are a little more difficult problems that always like to do it to take time as well. I don't expect to do any questions on what we've done so far? Section 2.1 is basically just talks about limits, limitations, and all the talk. 2.2 is going to look at numerical and graphical approaches. Then what? Then what we're doing before. We looked at tables, numerical approaches, and we looked at graphical approaches. Okay? So we're sort of doing the same type thing again. The goal of this section is to define limits and study them using numerical and graphical techniques. We begin with the following question. How do the values of alphabets behave when x equals a number t? Whether or not alpha t is defined. It may not be, but you want to know what how the function is doing as the question. So here is investigated and suggested control now go through that. This is what I'm going to do it graphically because I think it makes sense. I should have blown that up. Sorry, I'm counting. I want you to tell me, I've already sort of waved my arm and it's so slow now. Okay. I want you to tell me what a sine curve looks like. Where does it begin? 0, 0, and at pi halves it goes to 1. Negative pi halves, it goes to negative 1, and then it just goes up and down. That's basically what a sine curve is. A really ugly sine curve, okay? Just like that, right? It goes through 0, okay? Now, how about this function? F of x is equal to x. What's that? Y is equal to x. Not there, but the identity function. It's basically that. Even though they're approaching 0 there, they're close under the same configuration. Okay? That is an easier one to go through about it. It doesn't have to be exactly. Okay, exactly. So here's a function. F of x equals sine x over x. And the limit is x approaches 0 of that function is 1. The limit of x approaches 0 of this function is 1. Well, plug in as you go, on these ones, again, on both of them, when you're 0 and 0, that puts you at 1. But here's the beauty here, and then without making version. Okay. If you were to take your graphing calculator and graph that function, f of x equals sine x over x, here's what it looks like. And as you solve for what most of the time, here is our formal definition of a limit. We love formal definitions, don't we? It avoids us confusing with talking about very formal stuff. Okay. Assume that f of x finds that all x's are from open brackets, open brackets, Before we get to theorem 1, let's do a consequence. It says use that definition, this definition right here, to verify the following limit. The limit as x approaches 7 of 5. What do you reckon that might be? F of x is equal to 5. Can you describe that function to me? F of x is equal to 5. Maybe tell me how to draw it on a graph. Y is equal to 5. Very good. F of x is always y. Remember that. Great thing to remember. F of x equals y. Talk about this derivative here. That's the independent derivative, the dependent derivative. Where is y is equal to 5? Okay, here we go. So there it is. So guess what? No matter what x you put in there, y is always equal to 5. That's what we call a constant function, isn't it? Right? Now let's let x approach 7. What's your f of x approach? 5, because it's always 5. There's your function, okay? So sure enough, that limit as x approaches 7 of the function phi is equal to 5. Because the function f of the phi is always 5. No matter what your x is. Good thing to hang on to. Because believe it or not, we'll use that later. Okay? Not your phi. Okay? Now, let's do this. The limit as x approaches 4 of 3x plus 1. Someone give me an idea. Second? 13. You got it. Okay? And guess what? This is leading us to another little thing here. First thing is plug it in. So, from these two that you just did, here's an assumption. Okay? Appearance. Appearance. Any constant phase, any questions on those? Now, we're talking about graphical and numerical investigations. We've already been doing both of those. Okay? The numerical investigation has been set up tables and has to have the social work. So far, all of them have. Okay? For reasons they all will not. Okay? So far, everyone is doing it. Now, there are others that we will have to graphic. Clever enough to see the connection. What is the limit? I've written, but it hasn't shown up there. It shows up, okay? As x approaches 9 of x minus 9 over the square root of x minus 3. What is the first thing? What is happen to notice that I'm going to do a little substitution here. Is that all right? Let's do let. Give me another variable. I don't care what. It's not x. Say again? C? Okay, we'll use C. Let C equals the square root of x. Is that okay? I find the most complicated thing looking up there. Let's do a new variable. Then
What happens, how do we get this to be an X rather than a square? Square it, but then this would be C squared is equal to X. Would you agree with that? Okay? Now, let's plug that in. C squared minus 9 over square root of X C minus 3. Think of anything you might be able to do. Say again? Over what? Okay. Well, if you did that, okay. I think I hear what you're saying. Now we do the limit as C approaches 3 of this thing, and you have 9 minus 9 over 3 minus 3. You still get independent things. What is happening there? I don't know. All right. Here's something like that. I hope I won't get what is going on with this thing aggravates the screw out of me. Okay. Okay. What can we do with that numerator? That's C plus 3 times C minus 3 over C minus 3, and guess what? Now we can take the limit as C approaches 3, and what does that become? Sure or not? Fun. It takes a lot of work out of it. I think to be good in that, just a little theory out there. To be good in that, you just a little bit lazy. You ain't ever qualify. You got what? Now, the rest of you can still do it, but it helps you a little later, because guess what? All this difference is right? Trying to be a little lazy. One person, another person. Okay. It says investigated numerically, graphically and numerically. There they investigated it graphically. Here they investigated it numerically. Now you, you're out there.
if it's doable. Sometimes it won't be. But hey, me, anyway. Okay. Now, example 4, progression 205. This is not next one, you should, people study this, well, investigate this. Oh, here it is. Your limit as x approaches 4 of x squared. Set numerically and practically. I can tell. This is a look. Okay. So, they want you to do this just so you get the idea of what's going on there. Okay. Now, here's another. They call it a defining property of E. Everybody knows what E is, right? Visualization may have numerically progressive in favor of the flower time, but the natural base is E. And here's something that actually needs to verify. What is the limit as h approaches 0? What in the world is h here? Okay. As h approaches 0 of e to the h minus 1 over h.
that would be not right off the top. I need a timeout. Or maybe a time. Mind having one? Let's do a quick. Everything's so slow. I should have done that as soon as I clicked. Okay, I was trying to think if there was a way to think of this, and I'm not sure there is. X, or e to the h, or whatever you, that is a function that looks like in fact, now that I look at this, something seems a little off to me. Oh, no, I guess that's right. This is the graph of y is equal to e to the h. Okay. That's what y is equal to e to the x would look like. At 0, it's 1, you know, blah, blah, blah. Now, if you subtract 1 from that, it lowers it to this, okay? And then, so maybe this is going to work out. If that's compared to the identity function here, just like it was with sine x over x, it does look like the slope here and the slope there line up on top of each other, so that does look to be the case. So yeah, I think maybe you could do that. Interesting. This does not, okay. E to the x is this one. This one. E to the x minus 1 is this one. So e to the x minus 1 over x, or over e to the h minus 1, then it goes back looking almost like the same function we had to begin with. I never thought of that, but that's indeed what it looks like. But that's just a property of E. Now, like I said before, all the ones we've hit so far have had limits. Hang it up if you really think all of life is going to be that easy. It's not. And before I show the next slide, I want to do the next one. And I want to issue a warning as I do the next one. Goodness gracious, this is so slow. Okay. So this has nothing to do with this. Here's your fun. Investigate this. The limit as x approaches 0 of sine of pi over x. Okay? Now, if we were to proceed with this one, like we did before, and just start randomly plugging in numbers, if I ask you to set up a table, x and sine pi over x, okay? If I ask you to give me some values for x, and we want x to be approaching 0, so let's do it from the left, let's do it from the right. let's do as x approaches 0 from the left-hand side as x approaches 0 from the right-hand side. If I ask you to give me some x's to plug in there, what would you give me? -1? Second? Okay, you're getting further from 0. Let's get closer to 0. Huh? Okay, we start at -1. What would be another one? Negative point what? This is 0.1. Okay, negative 0.01. That's getting closer to 0, isn't it? Would that be reasonable? It's a lot like what the book did. How about from the right-hand side? 1. 0.1. 0.01. 0.001. Okay. Sound reasonable. If anyone has a calculator, plug in some of those. Be sure you're in radian mode. The pi sort of gives that away. You don't want that in degrees. Okay? This would be sine of minus pi, right? Pi divided by -1 minus pi. What would that be? I can do that one, I think. Sine of minus pi. Oh, pull out the boxes. Sine of minus pi. It's going to take longer than I thought, okay? Anyone know what sine of minus pi is? Let's do our good old sine curve again. Starts at 0 at pi halves. It goes to 1. At pi, it goes down to 0. 3 halves pi. It's -1. Over here, it's go down to -1, minus pi halves. At minus pi, it's back up at 0. And it just keeps the same pattern going, right? At the half pies, it's at your max or your min. At the pies, it's zeros, right? Minus pi is 0. Plus pi is 0. Any pi is 0. 7 pi is 0. 45 pi is 0. And if you plug these values in, this is -0.1 here. Move it upstairs, that becomes a -10, right? 1 over -0.1 is 10. That would be -10 pi. -10 pi is 0. At 10 pi, it's 0. At 100 pi, it's 0. At 1,000 pi, it's 0. Okay? All these would be 0. So you'd look at that and say, hey, this is going to 0, isn't it? No, it isn't. And here's why. Because you have chosen values that made whole numbers. And sine of a whole number of pi's, no matter what that whole number is, infinitely small, infinitely large is always 0. But do something that gives you something else, like negative 0.3. Let's see. I think that would work. No, yeah, -0.3. Then you'll find it's not 0. Okay, and -0.00003. Would not be 0. Don't do any of this. Okay. Start by looking at this. What is that form? Forget about the sign now. What is that form as x is approaching 0? Say again? Indeterminate. Not indeterminate, because that's not a 0. That's an undefined form, not an indeterminate form. Indeterminate is 0 over 0. This would be pi over 0. Never, ever, ever defined. Anything other than 0 over 0, not defined. So basically, you're taking a sign of a number that has no limit. Well, if this is a positive number, here's what the sign does. It bounces between -1 and 1, between -1 and 1, and it keeps doing that forever and ever. So what your sign of that is doing is going from -1 to 1, from -1 to 1. You just happen to pick some points here that were always the 0 points. This never ends. The closer you get to 0, the faster it goes from -1 to 1. So it doesn't have a limit anywhere. From the left-hand side, same thing. It's going from -1 to 1, and it takes on all the values between -1 and 1. And the closer you get to 0 from the left, then the faster and faster it takes on all those values. So no, this has no limit because your basic form has no limit. So don't try plugging in numerically. Don't try drawing it graphically. Or if you do, you'll go send your calculator strike kind of crazy. Look at the form. That's not indeterminate. That's undefined. Hang it up right there. You can't do it, okay? And books love to have you go through and do this other thing, which I just had you go through and do. Here's what it looks like. Oh, I'm sorry. This is the numerical form of the previous one. I forgot to show that. Sorry about it. Okay? And sure enough, this is e to the h over h. And that's getting closer and closer to 1 here, closer and closer to 1 there. Sorry. Forgot to do that. Here is this one. Okay? The closer you get to 0, this thing is going infinitely large, infinitely small from the left, infinitely large from the right. So it's changing values between plus or minus 1. So this is just going up and down, up and down, faster and faster and faster. The closer you get there, you burn a hole in the paper before you get to it. No, it's just a ridiculous question. And it's a ridiculous question because this form right here is undefined. Don't ever take a function of something that's undefined. You can't do it. It's not defined, so don't do it. So that graphically shows you it stays between plus and minus 1. Closer you get to 0, it just goes back and forth faster and faster. Notice how cleverly they decided to take different values this time, not 0.1, 0.01, 0.1, but picking numbers other than 1s. In fact, other than numbers that are, I'll say it, terminal decimals, okay? I mean, not terminal decimals, or a fraction of 0.03, that would be, pi over that would be the reciprocal of that as well. It wouldn't be a whole number, okay? These do not come out being, if you do 1 over this, it does not come out being a whole number. Any of those. If you did a 1 here or a 5 there, yeah, those are going to be whole numbers. But to some number that isn't going to come out that. And when you do that, you see you bounce all over the place between plus and minus 1. But that's not how they chose the numbers before, was it? They happened to choose those that were easy to calculate. You choose those here, you think it's all 0. Don't do it. Don't even get close to do it. Look at this and say, undefined, hang it up. If it's undefined, you can't take a sign of it. So why they have you do it numerically and graphically, you should just look at it and say, no, that's undefined. Stop there. Okay. Now, if you recall, if my thing ever comes up here, we usually would take a limit of something from the left and from the right and then go from there. Only if the limit is the same. Okay. This is a perfectly reasonable looking function, isn't it? What happens to that as x approaches 0? Numerator goes to 0, denominator goes to zero indeterminate form. So you think, hey, must have a limit, right? It's not an undefined form, it's indeterminate. No, can't say that either. Because this is what they call a piecewise defined function. Remember that? What is absolute value? I'm going to have to lose it when I do this. Absolute value of x is equal to x for x greater than 0 and minus x for x less than 0, right? And you can put the equal sign under either one of those or both of them. It doesn't matter. It'll be 0 there, okay? So let's take a look at that then. Then this f of x we got here would be x over x for x greater than 0 and x over minus x for x less than 0, right? What's x over x? Plus 1. What's x over minus x? Negative 1. So this has negative 1 for any x is less than 0. That has a limit of positive 1 for any x is greater than 0. As x gets closer and closer to 0, they each have limits, but they aren't the same values. So this does not have a limit. It has a left-hand limit, it has a right-hand limit. But those two limits are not the same, so it has no limit at x equals 0. It has a limit from the left as x approaches 0, a limit from the right as x approaches 0. But since those are not the same, it has no limit as x approaches 0. So this is what we call one-sided limits. Does have a limit from the left, it does have a limit from the right, but since those two limits are not the same, it does not have a limit just as x approaches 0. Does it from the right, it does it from the left, not otherwise. Okay. Probably should have preceded that with a little bit of verbiage. I just went straight to the graph. This was example 6. Okay? Now, that one I can express as a functional value. This one I can only express as a graphical illustration of a function. Okay? This is, again, a piecewise defined function. Okay? It looks like to me, coming from the left, this appears to be something like sine x over x. It doesn't seem to be the same, but something like that. Sine of pi over x, or something like that. Not defined. It has no limit as x approaches 0 from the left. It sorts back and forth between plus and minus 1, faster and faster and faster, so it has no limit. Approaches 0 from the right, though, it has a limit of 2. It does not define at 0, but it has a limit of 2. As x approaches 2 from the right, it has from the left, it has a limit of 3. Okay? But as x approaches 2 from the right, the limit is 1. Okay? Not defined at either of those. Okay? And as x approaches 4 from the left, that has a limit of 2, I think. And as x approaches 4 from the right, it also has a limit of 2. But it's not defined at x equals 4 either. So, limit as x approaches 0 from the left does have a right-hand limit as x approaches 0. 2, not defined at 0, but it has a limit there. It has a limit as x approaches 2 from the left of 3. It has a limit as x approaches 2 from the right of 1, but it has no limit as x approaches 2 without one-sided. Two-sided, it has no limit because those two limits are different. Not defined at x equal 4 either, but it has the same limit as x approaches 4 from the left and from the right, so it does have a limit as x approaches 4, period. That would be it too. Strange function, no about it. No limit, 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 limit. These two limits are not the same. Limit, limit. But those two limits are the same, so the x equals 4 will have 4, period. Both sides. Okay. You think you'll ever run into a function like that? I hope not. But if you did, there's characteristics of it. Okay. So, what they're getting at here, this function has no value at x equals 0, x equals 2, or x equals 4. Where else? Does it have a limit at those three places? Left-hand limit at 0? No. Right-hand limit at 0? Yes. Left-hand limit at 2? Yes. Right-hand limit at 2? Yes. But they're not the same, so it doesn't have a limit as x approaches 2 in general. Does it have a limit as x approaches 4? It doesn't have a value at x equals 4 as x approaches 4 from the left? Yes. From the right? Yes. And they are the same limit, so it does have a limit there. So, weird, but true. Now, the next little segment here is talking about infinite limits, which almost seems like they're a contradiction in terms, okay? But it just depends on how you define that, okay? Now, can't get all this on a Zoom, but we can get parts of it, okay? Let's get this part first. Okay. This is a function, f of x equals x1 over x minus 2. Now, back when you were in pre-calculus algebra, I bet you did things with that. What kind of function did you call that? N. It's the ratio of two polynomials. So we called it a rational function. Very good. When you dealt with rational functions, you look for asymptotes, zeros, intercepts, those kind of things. This has a vertical asymptote because guess what? You can never divide by 0. Okay? So x minus 2 cannot be 0, so means x cannot equal 2. There is I like to put cannot equal 2. X can never be 2. Okay? Now, horizontal asymptotes is the ratio of your leading terms. Okay? 1 over x, that ratio as x goes to infinity, the negative or positive, that's going to 0. So you have a horizontal asymptote of 0. Okay, they don't draw it in here, but it's a dotted line there on your x-axis. There is no y-intercept where x is equal to 0. Wait. I said that wrong. There is a y-intercept where x equals 0. That would be 1 over negative 2, so negative 1/2. There is no x-intercept because this thing can never equal 0. Y can't be 0 because 1 can't be 0. For this numerator will have to be 0. 1 can't be 0. So it has no x-intercept. It does have one y-intercept where x is equal to 0. And then from this, since you have your horizontal asymptote, your vertical asymptote, you have a point here, you know it has to be within that. You have to pick a point here, like 3, and 1 over 3 minus 2 would be 1. 1 over 1 would be 1, so 3, you're really at 1. So now you know you have to be in this spot. That's how you drew the graph here. Okay. You have a discontinuity at x equals 2, so there is no limit as x approaches 2. Is there a limit as x approaches 2 from the left? No, it's going to infinity. There is no limit there. aggravates the fool out of me. There, okay? Getting a little calmer about it, though. Does it have a limit as x approaches 2 from the right? No, it's going to infinity that way too. So it certainly has no limit as x approaches 2 anywhere. One-sided, two-sided, no-sided. There's no limits as x approaches 2. Everywhere else it is defined, and you have limits there. Okay. Another function, f of x equal 1 over x squared. Again, you start with your vertical asymptote. Your denominator cannot equal 0, so x squared cannot equal 0, meaning x cannot equal 0. Well, you don't see it, but there's a dotted line on the y-axis. Horizontal asymptote, ratio of the leading terms, and there you let x go to infinity, and that's going to 0. Okay? Notice here, as x goes to infinitely negative, this is approaching 0 from the upper side, because this is still positive, and from the right it's positive, so both of these are approaching there. And it's no y-intercept, because that can't be 0. No x-intercept, because 1 is not 0. So there's no intercepts at all. And you know this thing is always positive. And it's also an even function, so it reflects off the x-axis, so that's fine. So anyway, there is an asymptote here as x approaches 0 left, right, no limit anywhere as x approaches 0. All right. Okay. Now, here is another, okay. Here's a function, f of x is equal to log x. Have y'all dealt much with logs before? Lots or little or none at all? Natural logs. A little bit. Okay. Here's a hint. The log of 1 is always 0. Log of 1 is always 0. That comes because log is the inverse function to exponential. The exponential e to the 0 is always 1, so log of 1 is always 0. They're inverse functions of each other. Exponential function approaches 0 but never reaches 0. No matter how e to the x, as x gets incredibly negative, it's approaching 0 but never goes to 0. Well, similarly, flip that across the identity function here, and that means as x approaches 0, f of x approaches negative infinity, but never reaches 0. So log of 0 is never defined, ever. Okay? So there is no, you have a vertical asymptote at x equals 0. Okay? Approaches it but never gets there, so there is no limit as x approaches 0 of log x. None. It's going to negative infinity, never gets there. How about a horizontal asymptote? That looks like it's leveling off, sort of. Does it ever level off? Is there some limit here that of x, you can get an x big enough that you'll never exceed some value? No. It does get less and less of an increase, but it's still always increasing. Always. Less and less, but it's still always increasing forever. So this has no horizontal asymptote. Okay? It does have an x-intercept here, no y-intercept because it can't reach 0. It does have x equal 1, log x equal 0. So this has no limit as x approaches 0, and no limit as x approaches infinity. It just keeps increasing. Oh, yuck. That was example 8. I should have had you doing it rather than me doing it. I thought it was just defining it. These were your examples. Okay, that does finish 2.2. The summary here has a lot of bullets, so really pay attention to and look at those bullets there. Let's look at some preliminary questions, and what I think I'll do is find the slide without very much on it. This one doesn't have a lot on it. We'll do these questions here. What is the limit of f of x is equal to 1 as x approaches pi? The function f of x is equal to 1. What is the limit of that as x approaches pi? In other words, how do you write that in your limit statement? The limit as this goes down here. X approaches pi. And what's your function? 1. So that's what we're looking for. What is the answer to that? 1. Yes, because f of x equal 1, no matter what value x you put in there, it's equal to 1. You put pi in there, it's still equal to 1. So that is equal to 1. We hit that one earlier, remember? Okay, that's preliminary question 1. Let's do question 2. What is the limit of g of t equal t as t approaches pi? Second? Okay, that would be the limit as t approaches pi of t. Whoa. What would that be? A little louder? I'm hard of hearing. That would be pi. Because t is equal to pi, as t approaches pi, t is equal to pi. Almost redundant. Okay, number 3. Here's a question, the limit, that's a really ugly limit, isn't it? Yuck. Slow down, though, not write quite so fast. Okay, is the limit as x approaches 10 of the number 20 equal to 10 or 20? Or neither? Huh? A little louder. 20. Bingo, you got it. Oh, you can't say bingo in Alabama. Sorry. Okay, number 4. Can f of x approach a limit, it's a question, as, I can't write, as x approaches c if f of c is undefined? Okay. If so, give an example. I really don't like the question. Okay? It is a good question. It's a legitimate question. I would have rather said if f of z of c has no value given. Okay? Because when I read undefined, I think that's as opposed to indeterminate. It could be if f is indeterminate, f of c is indeterminate, but if f of c is undefined, my definition, that never exists. Okay? But they're not using undefined that way, is f of c does not have a value. That's what they're doing. So what's your answer? Yes or no? Okay. My definition of undefined, it would be no. Their definition of undefined means that it just doesn't have a value, then it could. Okay? For instance, the one, like we said, I'll just make up one, x squared minus 4 over x minus 2. That's, according to their definition, undefined because x can't be 2, right? Okay. And it can't be 2. It has no value at x equal 2. But I still don't call that undefined. I call it indeterminate. But the book doesn't make that distinction. I do. So that does have a limit. What would that limit be? The little trick I showed you. What's your F word? Factor. X plus 2 times x minus 2 over x minus 2. These go out, and as x approaches 2, what do you have? That thing is equal to 4. So yes, f can approach a limit as x approaches, in this case, 2, even if f of 2 is, you can't do it because it has a denominator of 0. I didn't like it. But that's what they're getting at. I like to make a distinction between undefined and indeterminate. They're not making that difference. So this, let me just, I didn't check them. The first one's 1, the second one's pi, the third one's 20, and the fourth one is yes, but they didn't give an example. We did give an example. Okay, number 5. I think I'm going to need more space, so I'm going to erase all we got. Can I erase this yet, or y'all still copying? Okay. What does the following table suggest about the limit as x approaches 1 from the left of f of x, and the limit as x approaches 1 from the right of f of x? And here's the table. Got to find it. X, f of x. They do their table horizontally. Some things I like to do horizontal, but tables I prefer vertical, but that's fine. 0.9 is 7. 0.99 is 25. 0.999 is 4317. 1.1 is 3.0126. 1.01 is 3.0047. And 1.001 is 3.003000011. Okay. That table, What does that suggest about the limit of f of x as x approaches 1 from the minus side? Say again? Okay. Here's 0.9, that's 1/10 off. Here's 100th off. Here's 1,000th off. You're getting closer and closer to 1. What's your f of x doing? Blowing up. It looks like it's going to infinity. So I would say this does not exist. D, N, E. Like D and R only do. Okay. Now, how about as x approaches 1 from the positive side? As it gets closer and closer to 1 from the positive side, what does f of x appear to be doing? That's getting closer and closer to 3. I would tie that. So I would say the limit from the left exists, from the left does not exist, from the right is 3. Would you buy that? You see how they get that? The limit on the left side of 1, the closer and closer you get to 1, the bigger the number gets. I mean, it gets bigger, okay? Doesn't seem to be approaching a limit. Seems to be going to positive infinity. But as x is approaching 1 from the left-hand side, it's getting closer and closer and closer to 3. I would say that limit's probably 3. Did you buy that? Okay. 2.2, going to infinity. I don't even like to put the symbol there. They do. And from the positive side, it's approaching 3. Okay. Number 6. Can you tell whether, this is 5, number 6. Can you tell whether the limit as x approaches 5 of f of x exists from a plot of f of x for x greater than 5? Boy. Can you tell the limit, if the limit of f of x exists, as x approaches 5 exists, from a plot of f of x for x greater than 5? Can you tell if that exists or not? If I said this, I would say yes. Can you tell whether that exists? Yes, you can. If you have a plot of everything greater than 5, and as it's getting closer and closer to 5, you have everything up to there, but you don't have a value at 5, you can tell me either where it doesn't exist, or if it does, what the value is. But without the plus here, you can't, because you don't know what's happening from the minus side. And for the limit, without a symbol here, you have to know it from both sides, and they have to be the same. So no, you can't tell this, if that exists or not, if you only know what's happening on the right-hand side of 5. You have to know what's happening on the left and right. If you go back to our first thing, remember it has to be some interval containing C, even if it doesn't exist at C. So you have to have C inside the interval, not at the edge of the interval. You have to have it in the whole interval. So the answer for that is no. Without that plus there, you can't tell, if all you know are the right-hand sides. So number 6 should be no, and it is no. Now, can I get 7 on here? No, I can't even write 7. Well, I probably could, but it would be too crowded. So what I'll do is erase all the ink, and let's do number 7. If you know in advance that the limit as x approaches 5 of f of x exists, you know that it does exist. Know that. Can you determine its value from a plot? I wish I had read this. Of f, I've lost it, of f of x for x greater than 5. Okay. Same question as before, except this time you already know that limit exists. You don't know what it is, but you know it exists as x approaches 5, meaning both sides has to be that. You know that limit exists. Then can you determine its value if all your plot shows is the right-hand side of 5? If you already know f of s does exist at x equals 5, as x approaches 5, not at x equals 5, but as x approaches 5, from right and left, can you determine its value if all you know is what's coming at it from the right? Yes. Because if this exists, without a plus or a minus here, that means they have to be the same, like these two. Okay? So if all you knew was this, and you knew that limit does exist, then you knew it had to be the same thing from the other side. Okay? So that one is a yes. If you already know it exists, you just don't know its value. If all you have is one side or the other, it's got to be the same on the other side, if that limit exists. Because if it was different on the other side, the limit wouldn't exist. So that one is a yes. Good deal. Homework exercises here. Do either 1 or 3, or both. Do number 5. Do number 7. Do any of the odds 9 through 15. And do any of the odds 17 through 35. And it has a whole bunch of those. Okay? Do 37. And then do any of the odds 39 to 45. Do 47. And any of the odds 49, or either 49 or 51, or both. Do 53. Another weird one like that one. Not quite that weird, but similar. And then do any of the odds 55 to 59. And either 61 or 63. Now, time out here. In the further insights and challenges, the very first one talks about a Fraunhofer diffraction pattern, which is really a little more physics than it is math, but if it's something you want to pursue, that might give you a potential paper topic. So you might want to look at that. The rest of them, it's up to you. Okay. What have we got? About 3 minutes left. And I kind of hate to do this to you, but I don't think we can get very much covered in the next 3 minutes. So I would say let's just end it there. We'll pick up at 2.3 next time. Okay? And I asked one when we were in the hallway or elsewhere if he thought the pace was too fast, too slow, or okay. What do y'all think? Am I dragging this out too much, or am I going too fast, or is it all right? Huh? It's okay. All right. Sometimes I get carried away. Sometimes I follow the slides and then realize that should have been an exercise and we should have done that first. But I'll try not to do that. All right, pick up at 2.3 next time. Good deal. We will see you Thursday. Okay. We actually have 2 classes this week. Isn't that nice? Okay. Yes, sir. Oh, I'm sorry. This is just because it's the second day of the week. Next week, we'll have 2 classes finally in 1 week. Last week 1, this week 1. From now on, it'll be 2. Yeah. Yes, sir.
Was that the new role, or was that from the same last week?
Okay, so this one more time.
On the roll, is that the same from last week, or is it this week's new roll?
The roll?
Yeah, because when I paid for the class on the 24th,
Yeah.
and then for some reason I checked my bank account to see if they charged it.
Right.
They charged it the day I paid for it, and then the next day I checked my accounts, and then it didn't say charge me at all.
Oh, so you got it for free. There you go. Okay. I don't know. No, this is the one I printed out last time. I haven't looked at it. I can do that quickly. In fact, to keep from recording this,